Hello all, this is part 4 of chapter 6, the second law of thermodynamics, and this is the last part of the chapter itself. After this we will have 2 additional parts going over some sample problems. Okay, so in the previous slides we talked about the concept of heat engine and the concept of a heat pump or refrigerator. So in the case of a heat engine, so you see the schematic on the left here. So we said that the heat engine is like a black box interacting with a source which provides heat on the top, and also a sink whose job is to accept rejected heat. So heat coming in, QH comes in, QL goes out. As a result of this process, the heat engine actually is able to produce a net amount of work. So in other words, QH amount of energy comes in, the heat engine is able to produce W net out, and the rest of it, QH minus W net out, which is equal to QL, has to be rejected to the environment, to the sink. So now the question is that, all right, so how about this black box, the heat engine, inside of this heat engine itself? How to model it thermodynamically? So a French engineer, Carnot, has come up with ideal processes, 4 ideal processes, in order to model the heat engine. So these processes are ideal, meaning that the heat engine working based on these processes is able to produce the maximum amount of work per QH. So is able to produce, to have the maximum efficiency. Given that TL, the temperature of the sink, and TH, the temperature of the source, remain the same, fixed. Okay, so now let's look at the Carnot cycle, and its job is to model a heat engine. So we have shown the process on a PV diagram, and on the left, in the middle, we see the details, some details of each process. So first, from 1 to 2, state 1 is like the initial state. So when the process starts. So here we have modeled it using a piston cylinder arrangement, which can best actually serve the purpose, but it doesn't have to be a piston cylinder. It can be a thermal power plant and so on. So now let's say the piston is at point 1 and we provide heat from the source to the gas. So in order to keep this process reversible, there should be no temperature difference between the sink and the gas. So both of them are kept at TH. As a result, this heat transfer process remains reversible. Then the piston expands from 1 all the way to 2. And we can show it on a PV diagram. It's a constant temperature or isothermal process. So then we reach to point 2. So process 1 is therefore reversible isothermal expansion. Then from process 2 to 3, we remove the heat transfer process and then let the piston expand from TH, gas temperature TH, to TL. So this process 2 to 3 remains adiabatic. There is no heat transfer, the system is insulated, but we do have expansion. And this adiabatic expansion is reversible. It means that there is no friction. It's a very slow quasi-equilibrium process from TH to TL. So this reversible adiabatic process, we will see that later in chapter 7. This is called an isentropic or entropy constant process. Reversible adiabatic from 2 to 3. All right. Then let's move to process 3 to 4. So from 3 to 4, it occurs at constant temperature again. So from 3 to 4, the temperature remains constant during this process, and the gas rejects heat from the gas itself from the cylinder to a sink. So QL amount of heat is rejected from the gas to the surrounding at constant temperature. So TL is TL of the gas is the same as TL of the sink. So this is a reversible heat transfer process. So process 3 is therefore reversible isothermal or constant temperature compression. So we are compressing the gas back to in the direction of the original state. Then we get to the process 4 to 1, and from 4 to 1 the temperature TL is going to jump back to TH in order to reach point 1. So process 4 to 1 is also reversible, and it is adiabatic compression. So during process 4 to 1, so 4 to 1, as you see, the system is insulated, so it's adiabatic. And as a result of compression, the temperature gradually increases from TL to TH. So 4-1 process is reversible, adiabatic, therefore it is also isentropic or entropy constant. So what you see on the PV diagram is the process paths from 1 to 2, 2 to 3, 3 to 4, and 4 to 1. On the diagram, you see QH added to the cycle, QL rejected from the cycle, and the area enclosed between all of these 4 processes is the W net out. And QH minus QL is equal to W net out according to the first law of thermodynamics. So this is the description of the Carnot cycle, which is used to model a heat engine. So in addition to heat engines, we talked about heat pumps or refrigerators. So this is again the PV diagram of a heat engine that we just had in the previous slide. And then if we reverse all processes, if we change the direction of the arrows that you see for heat engine, and including the direction of the QL and QH, so you see that if you change the direction of QL, so that's the QL extracted or pumped from a refrigerated space, and then W net amount of work in has to be performed, for instance, by the compressor. So the sum of this QL and W net in equals QH. So the heat given, for instance, rejected to the condenser in the case of refrigerator, or QH given to the interior of the house in the case of a heat pump, if the purpose is to heat the house. So therefore the reverse Carnot cycle is very similar to, or the same as, essentially the same as the Carnot cycle, except that we would need to change the direction of the arrows. So if you reverse all of this, so for instance here from point 1 to 2, this is in the case of a refrigerator, from point 1 to 2, that's where the gas enters the compressor. So this process 1 to 2 is therefore reversible and also adiabatic, so it's isentropic. From 2 to 3, I'm sorry, so here, so from sorry about that. So if you look at point 1, this is the exit of the condenser. So at the exit of the condenser, the pressure is high, the temperature is high. So let me correct myself about the reverse Carnot cycle here. So at point 1, that's the exit of the condenser. It enters the throttling valve. in order to break down the pressure in an ideally isentropic process. So it's reversible adiabatic. At point 2, it is ready to enter the evaporator. In the evaporator, it receives or extracts QL. And then at point 3, it enters the compressor, which is again reversible and adiabatic, and therefore isentropic, entropy constant. In this chapter, we have not talked about entropy yet, but I'm just talking about it so that you become familiar beforehand. So from 3 to 4, the compressor compresses the gas in a reversible adiabatic process, and then at point 4, the gas enters the condenser and rejects QH to the surrounding. So this is the reverse Carnot cycle, sometimes called the refrigeration cycle as well. So for a refrigerator to model, these processes are most efficient, are ideal to model a refrigerator or a heat pump. So here W net in is the work needed by the compressor, QL is the extracted heat from the colder surface, colder space, and QH, which is sum of W net in and QL, is the heat rejected either in the condenser or in the interior of a house. All right, so there are two Carnot principles related to the Carnot cycle. So one is that these are listed here. So this should be explained in regard to this schematic. So the number one principle is that the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same two reservoirs. All right, now let's look at this schematic. Same two reservoirs, the one source and the sink, these are the same. Now we do have 3 heat engines. So one of them is irreversible, the other 2 are reversible. So principle 1 says that the efficiency of the irreversible cycle, eta thermal 1, must be less than the efficiency of the reversible cycle 2, because by definition we claim that, which is physically also meaningful, that the reversible cycle, which is the Carnot cycle, is the most efficient. So any other real cycle would be, its efficiency would be less than the efficiency of the Carnot cycle. So eta TH1 is less than eta TH2 based on principle 1. Principle 2 states that the efficiencies of all reversible heat engines operating between the same 2 reservoirs are the same. So if heat engine 2 and heat engine 3, both of them are reversible, so even if one of them is smaller, one of them is larger, but both of them are interacting with the same source and the same sink. If both of them are reversible, then their efficiency must be equal. So eta theta 2 is equal to eta thermal 2 is equal to eta thermal 3. So that's principle 2. Principle 2 is also shown on the right schematic. The source is at temperature of 1000 Kelvin. The sink is at temperature of 300 Kelvin. So both heat engines A and B, both of them are reversible. So principle 2 mandates that the efficiency of both of these heat engines are equal. And we will show that the efficiency is equal to 70%, given that the sink temperature is 300 and source temperature is 1000 Kelvin. So now we want to prove that based on these two principles, actually we can prove that the efficiency of the reversible cycle can be simplified. So for any heat engine, So for any heat engine, we showed that the thermal efficiency is equal to 1 minus QL over QH, previous lectures. Or this is equal to W net out divided by QH. So therefore, the efficiency of any heat engine is equal to 1 minus QL over QH. We can prove that for a Carnot cycle, which is the ideal cycle, QL over QH is actually equal to TL over TH, where these temperatures are given in absolute temperature Kelvin. That's why here we showed them in Kelvin. 1000 Kelvin, 300 Kelvin. So if you do have a heat engine, which is the most ideal, it follows the Carnot principle or Carnot cycle modeling all reversible processes, the efficiency, the maximum, the efficiency of that cycle is 1 minus TL over TH. So it means that in this case, the efficiency would be 1 minus 300 over 1000 or 1 minus 0.3 or 70%. So again, this equation is good for any heat engine, reversible or irreversible, ideal or non-ideal. And the one on the right, this one, is only good for the theoretical limit. So that's the maximum possible efficiency of a heat engine. That heat engine could be a power plant, could be an internal combustion engine, and you see that it's essentially not possible to have a heat engine whose efficiency is 100% because we always have a ratio of TL over TH non-zero. Alright, so how to prove this? How to prove that the efficiency of a Carnot cycle is equal to 1 minus TL over TH? So the proof is actually, I've written the proof here. It is pretty much straightforward. A couple of mathematical steps that we need to follow. So I just skip this one. So for those who are interested, they could just follow the slides from the beginning. So starting from the fact that for the proof of this, for the proof that QH over QL is equal to TH over TL, we need to consider 3 heat pumps, all of them reversible, one operating between T1 and T3, source and sink. That would be heat pipe C. That would be the heat engine C, and then another one between T1 and an imaginary temperature T2, and the third one would be between imaginary temperature T2 as the source and the temperature T3 of the sink. So based on this, you could follow the steps, and we end up with this mathematical reasoning and conclusion that for a Carnot cycle, for an ideal reversible cycle, the ratio of QH over QL must be equal to temperature of the source T sub H divided by temperature of the sink T sub L. So that's basically the proof that the efficiency of the heat engine in a Carnot cycle would be 1 minus TL over TH. So now the question is that so we said that this temperature T sub H and T sub L, this must be in absolute scale temperature or absolute temperature, which is the Kelvin scale. So we are already familiar with the Kelvin scale from previous chapters, but this is like a more formal or sophisticated way of coming up with the Kelvin scale. So basically, when we show that QH over QL is equal to the temperature of the source divided by the temperature of the sink, the question is that could we go ahead and use temperatures in Fahrenheit or Celsius? The answer is that no, because both of these temperatures have like an arbitrary point for 0 degrees Fahrenheit and 0 degrees Celsius. So it means that this arbitrary 0 point, this causes a problem, because you really want to associate no heat transfer with an absolute temperature, absolute 0. So for this purpose, we do need to develop, we do need to come up with a temperature scale which starts from absolute 0. So there is no negative temperature, because in this relation, as you see, the temperature cannot become negative. So it must, the temperature, this temperature scale that we use has to actually start from absolute 0, no negative. All right, so for this purpose, we can actually choose. So what is chosen? What is, the convention in thermodynamics is that the Celsius system is used, and then we try to figure out, modify it so that actually the Celsius system starts from absolute 0. So then that becomes the Kelvin scale. So how to do that, how to start from the Celsius, a Celsius thermometer, and convert it to a Kelvin thermometer. This is what we want to do. We want to start from the Celsius thermometer, convert it to Kelvin thermometer. How to do that? Well, this has been done a long time ago. So based on the ideal gas law. At that time, people still didn't know the complete form of the ideal gas law. It was called the Boles law. So based on the Boles law, for a gas at a given temperature, at constant temperature, so a gas at constant temperature and fixed mass, long time ago scientists had realized that the multiplication of pressure and volume of the gas in a container, PV, was a constant. Experimentally, they were able to show that PV for constant temperature and constant mass was a constant. If we compare it with the ideal gas law, where PV is equal to mRT, if temperature is constant, doesn't change, and mass doesn't change, the ideal gas law also mandates that PV is a constant. So Boyle's law is basically a consequence of the ideal gas law. Okay, so now how to establish the Kelvin thermometer according to the following experiment. So let's start with so let's say we do have a centigrade or Celsius thermometer. All right, so and we do have, we can determine the quantity PV of a fixed mass of a gas. So we start from a fixed mass of a gas, but we vary the temperature and then plot a graph of PV against temperature. So that means that the mass is fixed. So let's say you do have a gas in a container. So you let the volume change and also the pressure changes. So you could measure the pressure and also the volume. So I believe you could assume like a piston cylinder arrangement, frictionless. So an arrangement where you allow a variation in both pressure or volume, or you just let one of them to change and the other one is fixed. So the bottom line is that you should be able to measure pressure of the gas and the volume of the gas. If you want to keep the volume fixed, it's fine. Then the pressure changes, and using a pressure gauge, you could measure pressure and find PV. Anyway, so how to start from a Celsius thermometer? So let's say we do have a Celsius thermometer attached to our container in order to measure the temperature. For a given temperature, for instance, we can go ahead and measure P and V and calculate PV, therefore we would have 1 point here. So based on Celsius, let's say 80 degrees C. Then if we cool down the gas so that the temperature comes down at a lower value, let's say 30 degrees C here. At this 30 degrees C, we can go ahead and measure and calculate the value of PV again in order to have the second point. So now if we have multiple points here on the Celsius thermometer or temperature scale, then we can go ahead and extrapolate. The thing is that we really cannot decrease the temperature so much, especially a long time ago when this was established, people were not able to cool down the temperature. So for this to happen, we would need to have cryogenic systems, very strong refrigerators in order to reduce the temperature to go close to absolute zero. Even now, it is very difficult to get close to like absolute zero. So therefore based on these multiple data points, and given the fact that PV changes linearly with the temperature from this ideal gas law, PV and T, the temperature, they change linearly. So we just would need to, we know that the value of MR, the slope of the line, is a constant. Now if we attach several points and extrapolate, extend the line, then it will intersect the x-axis at the point here. In this point, if we calculate it, this is geometry, right? Algebra geometry. If we calculate it, this is equal to minus 273.15 degrees C. So that's why when we want to convert the Celsius degrees to Kelvin, we just say that Celsius is equal to Kelvin minus 273.15. In other words, this minus 273 degrees C becomes the origin of the Kelvin scale. So the Kelvin scale starts right from here. So if you want to get the Kelvin scale, it means that you would need to add 273.15 to centigrade. So it's like a shift. So it's like the difference between Celsius and Kelvin is just a shift in the x-axis. So that's it. So therefore the absolute zero, the lowest possible temperature, was obtained a kind of intuitively long time ago. Now experiments show that we can actually get very close to absolute zero. So therefore, as you see, the concept of the Carnot cycle helped develop the Kelvin temperature scale as well. Okay, so now back to the Carnot heat engine. So what you see here on the left, we do have a Carnot cycle. QH coming from the source and then QL going to the sink. We don't know QH and QL, but we do know the temperature of the source and the sink. Therefore, the efficiency, thermal efficiency of this Carnot cycle is 1 minus T sub L over T sub H, which is 1 minus 300 over 1000, 70%. So we can conclude that if we have a reversible cycle, the reversible cycle will have the maximum efficiency when the temperature of the source and the sink are the same. Then we can have countless number of irreversible machines, irreversible heat engines. So the efficiency of any irreversible heat engine will be less than the efficiency of the reversible one, because the efficiency of the reversible heat engine is the maximum. That's the theoretical limit. So in this case, it's 70%. Any actual heat engine will have an efficiency less than 70%. And it is also impossible to have a heat engine with an efficiency higher than the efficiency of the Carnot cycle. So the efficiency of the Carnot cycle is 70%. So if someone comes and claims that I have manufactured an automobile which has an efficiency higher than a value, a limit, some experts in thermodynamics can go ahead and do some calculations and figure out whether this claim is actually valid or not. So in summary, the efficiency of a heat engine, the efficiency is always less than the efficiency of the reversible cycle if the heat engine is irreversible. So it is equal to the efficiency of the reversible or Carnot cycle if the heat engine is reversible, and it is impossible to have an efficiency which is higher than the efficiency of the reversible cycle. So it is impossible to have an efficiency higher than the efficiency of the reversible cycle. That's impossible. Okay, so getting close to the end of this chapter. So since we established that the efficiency of a Carnot cycle is equal to Carnot cycle, which is for a heat engine, not for the heat pumps and refrigerators, the efficiency would be different. That we will have it in the next slide. So efficiency of a reversible cycle is 1 minus TL over TH. So then what can we say about how to increase or improve the efficiency? If this is the schematic of the heat engine reversible, it is at TH for the source and TL is fixed at 303 Kelvin. This is like 30 degrees C. So now the efficiency is 1 minus TL, which is fixed, over TH. You can see from this equation that if you increase TH, the temperature of the source, then if you increase the temperature of the source from in this direction, you see that the efficiency of the cycle increases. So the higher the temperature of the source, the high temperature reservoir, the higher the efficiency of the cycle. And this is shown here. So as you increase the temperature, the temperature of the source, the efficiency of the heat engine increases. So based on this, we can claim that the quality of the thermal energy increases with an increase in its temperature. So you remember that before we said that quality of mechanical form of energy such as kinetic energy and potential energy and pressure part of the energy is the best, highest quality, because they can perform mechanical work. And we said that the quality of the internal energy is the lowest compared to kinetic energy, potential energy. Now here we see that we can increase and improve the quality of the internal energy by increasing the temperature of the fluid, the gas, for instance. So in this case, it means that if we increase the temperature of the source, the efficiency will increase. Okay. So, and finally, so far we talked about the Carnot cycle and the efficiency of the Carnot cycle. How about the reverse Carnot cycle or the refrigerator and heat pump Carnot cycle? So in such cases, we do not define efficiency. Instead, you remember we define COP, coefficient of performance, of a refrigerator. So in the refrigerator mode, coefficient of performance was 1 over QH over QL minus 1. If we expect it to work as a heat pump, then the coefficient of performance is different, very similar but slightly different, 1 over 1 minus Q sub L over Q sub H. Okay. So this is general. This is any refrigerator or any heat pump. So if we deal with a ideal refrigerator and ideal heat pump, which is like it follows the reverse Carnot cycle, then we can go ahead and replace QH over QL by TH over TL. Or we can go ahead and replace QL over QH by TL over TH. As a result, we end up with this final equations for the COP maximum, the limit of a heat pump reversible and COP of a refrigerator reversible. That's the theoretical limit. So it means that we cannot make or construct a refrigerator with a COP higher than the value obtained from this equation based on given TL and TH. So what is this TL and TH for a refrigerator? For instance, in your household refrigerator, you can say that TL is the temperature, the design temperature of the inner compartment. How cold you want to keep the temperature of the inner compartment. TH would be usually the room temperature for the household refrigerator because the heat is rejected to the ambient, and TH would be the room temperature. So that's it. So what you see here if about the values of COPs. So here is a reversible refrigerator between 300 Kelvin and 275 Kelvin. That's what I talked about. So you see the ambient room temperature about 300 Kelvin and 275 Kelvin is this is 2 degrees C. This is actually the temperature of most refrigerators. It's slightly above the freezing point. So for this, if we go ahead and calculate the COP for refrigeration based on reversible cycle, based on this equation, we will get COPR equal to 11. Just plug in these numbers, 300 and 275 here. In the COP of refrigerator, you will end up with 11. So this 11 is the best efficiency that you can get from a refrigerator. In reality, the refrigerators therefore must have a COP less than 11. So for instance, 7. And it is impossible to construct a refrigerator working between 275 Kelvin and 300 Kelvin with a COPR greater than 11. So this 13, COP of 13 is simply impossible. Okay, so this brings us to the end of this presentation and to the end of this chapter. So we will continue with 2 more parts, solving a couple of problems in order to clarify some other concepts and how to apply these equations to solve problems. Okay, thank you very much for your attention.